Vertutscht, as they say. All of a sudden, it has been fixed. I had full confidence in the Institute for Theoretical Physics, as I said. I have a slide up there, and maybe I can have a little bit of light so I can see. I don't like to sit down. So if you give me a little light now, the question is, can you give a little light? And the answer is no, but that's okay. So I'll divide my talk into several portions. I'll talk about the history of lepton-hadron symmetry. That's a brief talk that I gave actually at the European Physical Society meeting in France, but you were not all in France at the time. But if you were, bear with me. The second part of the talk will be on a subject called Are Neutrinos Secret Sharers? And by that I will mean, are there some neutrinos look so different from quarks and so different from the charged leptons, but can they have some hidden properties in common? And one of those properties could be disparity in mass, and another property that they could have in common is to have nearly diagonal mass matrices. We'll come and talk about that in a moment. And then third, there's been a certain amount of attention recently from the report by a group at CERN that alleges that neutrinos pretend to travel faster than the speed of light. And we will discuss that pretense later. I'll say a few remarks about neutrinos and such before opera and after opera. And of course, this is dedicated to the opening act. And I think there's one button here that I push, and it does something. Oh, how wonderful. This is a new opportunity for me. I've never before used this electronic crap to give talks with. I have to turn this page, too. The history of lepton-hadron symmetry. This is conveniently divided into 5 eras, and the first era begins in 1917. Why 1917? Because that was the year that Rutherford managed to bang nuclei together and extract protons from small nuclei. So it was recognized that we now had 2 elementary particles, electrons and the nuclei, which Rutherford had discovered in 1913, the nucleus of the hydrogen atom. So from the period 1917 to 1932, when the neutron was discovered, we had the 1 + 1 era. There was 1 hadron, the proton, and 1 lepton, the electron. And people were furiously model building in a sort of senseless way. There was the nucleus surrounded by various quantum mechanical electrons, which were doing their thing according to Bohr and later on according to Schrödinger and all those other people. But then there was the nucleus, and the nucleus had to be made of the only known particles, which were protons and electrons. And so there was an age of a kind of attempt to give electrons 2 functions within the atom. One was the outside, the chemical properties of the atom. The other was inside, to give the nucleus the correct electric charge. Of course, that posed many problems, and there's a long story in which Pauli played a signal role and neutrinos were introduced, but we're not going to talk about that today. In 1932 to 1948, 1932 because the neutron had been discovered, we then had a doublet of hadrons. Oh, by the way, in those days, the word hadron and the word lepton did not yet exist, so we are a little bit out of time when I use those words. The second age was the age of 2 hadrons and 2 leptons, the proton and the neutron, and the electron, together with Pauli's originally neutron, which later became a neutrino, which later became an antineutrino, which even later became the electron antineutrino. But anyway, at that time, there were 2 hadrons and 2 leptons, 32 to 48. Then we come to a brief period from 1959 to 1963, where the 2+2 era led to the 3+3 era, and we had Bob Marshak, a delightful old friend of many of us, who proposed at the Kiev conference, which of course I could not go to because I was not. It's a terrible thing about those conferences. In the early days, the conferences were interesting, and I couldn't go because I wasn't mature enough. And then conferences became very boring, and I could go if I wanted to, but I didn't want to anymore. Anyway, the key of symmetry was the Sakata triplet of hadrons, the proton, neutron, and lambda hyperon, which some people regarded as the fundamental fermions. And they were likened to the lepton triplet of the neutrino, the electron, and the mu. It was a cute idea, this Kiev symmetry. It was a short-lived era. Sakata's triplet was replaced by 3 quarks. That was fine. But the discovery of the second neutrino in 1963 put an end to the Kiev symmetry. Or maybe it was 1962, Schwartz and Lederman and Steinberger. The next era, I would say, is from 1964 to 1965. And it began in Copenhagen when I was visiting Copenhagen, and so also was James Bjorkane. And we were playing around and rather playfully introduced a 4th quark, which we call the charm quark, which we introduced on purely aesthetic grounds, which in retrospect made a lot of sense. There were 2 doublets of leptons, the electron and its neutrino, and the muon and its newly discovered neutrino. And there was 1 doublet of quarks, the proton quark, the up quark, and the down quark. And then there was the strange quark, which was, left all alone. And how much prettier it would be if it had a partner too. And so we introduced the charm quark to marry with the strange quark. And it looked very symmetric, and there were many beautiful aspects which we could not appreciate, but we just made that idle suggestion. Interestingly, such a suggestion was also made by Yasuo Hara at roughly the same time. But nobody took this idea seriously. There was no particular reason for anyone to believe in a 4th quark until we came back to the subject a few years later, namely John Iliopoulos, Luciano Maiani, and I. Nobody had touched that subject, and then we realized 2 things. First of all, that the charm quark could serve a very important purpose. It could enable the extension of the just beginning to appear electroweak theory to extend to quarks. Otherwise, it could not extend to quarks because we would be besieged by strangeness-changing neutral currents. And we realized that the charm quark lived up to its name, that the name that BJ and I chose for the quark was just right, because a charm is an amulet, is something you wear to avoid evil. And the evil in question was one that would not be recognized by readers of El País, but you all recognize it. The evil is called strangeness-changing neutral currents. And there aren't any of those, and it was known there weren't any of those. That, of course, was a lovely symmetric era, 4 quarks and 4 leptons, 2 families of quarks and leptons. 1 family was the relevant one, which is necessary for life on Earth. The other family was the irrelevant one. There was a balance between relevancy and irrelevancy until it was spoiled by Martin Pearl, who found the 3rd lepton, the tau lepton. And it's funny, when there were 3 quarks and 2 leptons, you had to bang people on the head to convince them that there was a 4th quark. But as soon as the 3rd charged lepton was discovered, everybody immediately believed there would be another neutrino and there would be 2 more quarks. And of course, they were found. And today we have a complete 6 plus 6 situation, 6 quarks and 6 leptons, and we may be stuck with that forevermore. That's the end of part one, the history of lepton-hadron symmetry, and I cannot sensibly imagine that you have any questions to ask about that, but if you do. Questions? No. I thought not. Are neutrinos secret sharers? Neutrino masses and mixings differ crazily from those of their charged cousins. Neutrino masses are tiny compared to those of quarks and leptons, and neutrinos get their mass presumably from a different mechanism. Well, we're not sure of that, but presumably get their masses from a different mechanism than do charged leptons and quarks. All quark mixing angles are small, while two of the neutrino angles are actually very large. Nonetheless, can there be some hidden attribute that is shared by all fundamental fermions? Let's first discuss the possibility, the issue of mass. And I show in that table, I've the three kinds of particles, up-type quarks, down-type quarks, and leptons. I've normalized their masses so that the heaviest one has mass 1, so the top quark mass is 1, the bottom quark mass is 1, the tau lepton mass is 1. And then we see the masses of the medium-massed particle is 0.008, and the smallest one is 0.00003. For the down-type quarks, with 1 being the bottom quark, the strange quark is 0.002, and the down quark is 0.0006. And for leptons, again, 1 for the tau lepton, 0.06, and 0.003. The indication is that the disparity is very large. And I have defined for your convenience a measure of disparity, which is the quantity twice the mass of the biggest minus the mass of the middle guy minus the mass of the smallest guy divided by the mass of the middle guy plus the mass of the smallest guy. Why is this a nice parameter? Because the smallest the d could be is 0. D is 0 if the three masses are equal to one another. Clearly, in principle, d can be arbitrarily large. And indeed, d is large for the case of up-type quarks, down-type quarks, and leptons. It is 250, 1,000, and 32, which are relatively large numbers. D equal to 1 is a breakpoint because d equal 1 is the minimal level of disparity, of there being a true level of disparity. If d is equal to 1, if d is less than 1, the neutrino masses do not satisfy triangle inequalities, which is an indicator, a minimal indicator of disparity. So, note, if d is much larger than 1, no, I would just note that it's larger than 1 for the cousins, which is obvious. Now, what do I say here? Can neutrino masses be as disparate as those of their charged cousins? Can mass disparity be a property that they have in common? And the answer is, to some extent, yes, but mostly no, because the disparity, d, given what we know about the differences of the squares of the neutrino masses from decades of work on neutrino oscillations, we know that d is bounded above by 11, compared with 32, a few hundred, and 1,000 for the other particles. So they can't be very disparate in the case of a normal neutrino mass hierarchy, and in the case of a inverted mass hierarchy. I hate that phrase. Let's just call it a twisted mass spectrum. 1.03, just a little bit more than 1, is the maximum level of disparity. You can't have much disparity. The answer is more or less no. The neutrinos cannot share that property particularly well. Now let me digress seemingly and mention 3 observable quantities. Sigma is the mass of the sum of the absolute values of the masses of the neutrinos. I'm leaving open the possibility that neutrinos bear Majorana phases. Sigma is bounded How well it's bounded depends upon which astrophysicist you choose to believe. The most radical of the astrophysicists will claim that the sum of the neutrino masses is bounded by 160 milli-electron volts. The least aggressive of our astrophysicist colleagues will say that the sum is bounded by 2 electron volts. So there's a bit of a disparity there, and it depends on which priors one is willing to accept, and I'm sure that the situation will become clearer in the future. But clearly, the answer to that question, what is sigma, will arise not from high-energy physics, but from astrophysics and cosmology. The second number is m sub beta, which is the root mean square mass of the electron neutrino, which Catherine is trying to measure, will be trying to measure when Catherine is operative. And let us recall that Catherine is not finished yet. It will be finished, I hope, soon. Its maximal sensitivity is 200 milli-electron volts at best. And if the mass if that number is less than 200, there's no hope of Catherine seeing it. And I can't imagine that anyone will do a endpoint experiment on tritium more sensitive than Catherine. So that will be end of an era, or probably for at least a century. Let's go on to m beta beta, and m beta beta may be the parameter governing neutrinoless double beta decay. I say maybe because we don't really know whether neutrino masses are, to use the insufferable language that people have adopted, Majorana masses or Dirac masses. I don't like that language because I would prefer to say the language of lepton number conserving neutrino masses or lepton number violating neutrino masses. And the discovery of neutrinoless double beta decay, if indeed it is discovered, will be not so interesting when phrased in terms of showing neutrinos are Majorana. Rather, they will have expunged one of our last seemingly absolute conservation laws, the conservation of lepton number, and that will be phrased that way, it will be a Nobel Prize-winning discovery. If it's discovered. Okay, now let us imagine that d is equal to 1, which is the minimal level of neutrino disparity. If that is true, the sigma is 115 MeV, really low. M beta is 29 milli-electron volts for the normal spectrum, and 100 milli-electron volts, 50 milli-electron volts in the other case. And no matter, those numbers are far too small to be detected at Catherine, and we know that M beta beta is necessarily even smaller. Basically, if there's any trace of neutrino disparity, if neutrinos are anything but approximately degenerate in mass, which is very difficult to imagine theoretically, but if there's any disparity at all, a number of experimenters, namely all those looking for neutrinoless double beta decay and all those who hope to work at Catherine, will be sorely disappointed. So, that's a sad story. But who knows? Maybe neutrino masses are nearly degenerate. What sort of neutrino masses, well, I have it here. What sort of neutrino masses would yield M beta greater than 200 MeV, making Catherine very happy and also making the double neutrino searches at least feasible? The neutrinos would have to be degenerate to within 3%, corresponding to a very tiny disparity, a disparity of d equal to 0.016, that number which can range from 0 to infinity. Really, 3% of degeneracy. Two of them really close together, and one of them 3% difference. That is interesting. There is a bit of tension there. Because this implies that sigma is bigger than 600 milli-electron volts, and that is in serious tension with some of the astrophysical constraints, which we may or may not have to take seriously. I would, you probably know better than I. So in any case, we have been led, if we insist on neutrino degeneracy, we're led to an interesting possibility, a possibility that I call the 1 plus Z neutrino mass matrix. You will remember that Tony Z years ago introduced a speculation, which he even had a model to yield, where the neutrino mass matrix was a 3 by 3 symmetric matrix, yes, with its diagonal elements equal to 0. And 1 plus Z model is the same matrix with a large 1 added to it. That is to say, it's the unit matrix plus a very small, I should really call it a 1 plus epsilon Z matrix. That would be nice, because then we would have a property, finally, that is shared by neutrinos and by their charged cousins. The property is that the neutrino mass matrix approximately commutes with the charged lepton mass matrix, imagined as diagonal. They're almost commuting, just like the up and down quark matrices almost commute with each other. In the latter case, because the angles are all small. In the former case, because the masses are all approximately equal. But it is a property, hidden property, that neutrinos may have in common with their charged cousins. By the way, this sort of matrix was first proposed a number of years ago by Ria Zuden, also by Bert Stech at Heidelberg. Is there a reasonable model which gives such a mass matrix? Not that I can find, so I don't know. Let me turn to the next subject that I will discuss in this brief celebratory talk, which is Seeking Departures from Special Relativity, Part 1, à la recherche de temps perdu, because I have to remind you that my best friend had been for many years Sidney Coleman. Some of his least famous papers, least good papers, were collaborations with me, both at the very beginning of his career when we were advocates of the Eightfold Way, and at the very end of his career when he was suffering from severe depression. And around 1998, we became interested in tests of the special theory of relativity. And what we did is we imagined a small departure from Lorentz invariant quantum field theory. So what we did is put small terms in the Lagrangian that were not Lorentz invariant, and we restricted them in two ways. We said, first of all, we want a renormalizable modification, just for no reason. We imposed that. And we also imposed the constraint that there is a coordinate system, a coordinate frame, hopefully close to the one in which we live, perhaps the coordinate frame of the black body radiation, at rest relative to the black body radiation. There is such a coordinate frame in which there is rotational symmetry. Of course, there isn't rotational symmetry in any other coordinate frame, consequently, but at least there is one frame with rotational symmetry. Then we found that the principal consequences of these violations of the special theory of relativity were changes in the maximum attainable velocities of particles. That is to say, you could assign arbitrarily different maximal attainable velocities to photons, which is their velocity through a vacuum, of course, to electrons, to protons, to neutrons, et cetera, et cetera. And when you would do that, when you would make small perturbations of the maximal attainable velocities, bizarre kinematic things arose. That is to say, the kinematics of various particle interactions became changed. For example, if the photon were superluminal, that is to say, if the velocity of light in vacuum were greater than the maximal attainable velocities of electrons, then energetic photons would decay into electron-positron pairs. And from that, you could get a very severe constraint on the maximal attainable velocity of photons compared to electrons. And so it went. What astounded us was the following. We were aware of the experiment by Lamoureux, the very sophisticated atomic physics experiment from the University of Washington, where they had the limits on Cm, which is the maximum attainable velocity either of nuclei or electrons. I'm not sure. I think electrons. From the difference between that and the photon velocity, the absolute magnitude thereof, was less than 6 times 10 to the minus 22, which is a spectacular confirmation of the theory of relativity. But we noticed that we could get an even more spectacular confirmation from the mere existence of cosmic ray protons with energies of 10 to the 19th electron volts. Because protons with energies of 10 to the 19th electron volts, if they were superluminal, that is to say, if the maximal attainable velocities of protons were a little bit bigger than the velocity of light, these would Cherenkov radiate. And when I say Cherenkov radiate, I do not mean it in the conventional sense. Well, I do, but I don't, in the sense that conventionally, when a superluminal electron, superluminal because light moves more slowly in a medium, is passing through gas, it radiates light. But it radiates light in a narrow frequency domain where the dispersion relation allows the light to be radiated. Things are very different here because we are assuming a fixed dispersion relation, and so one can radiate energy at all frequencies, and therefore the proton Cherenkov radiates at all frequencies, which means it loses most of its energy until it becomes subluminal very, very quickly and cannot travel more than a few meters, hardly could be expected to travel light years to get to the Earth. And the fact that we see those things gave us a limit even stronger than the Lamoureux limit. And so we have a bunch of very strong limits, including, in particular, the workers at Super Kamiokande used our analysis to show that neutrinos, electron neutrinos and muon neutrinos could not differ in velocity by more than 6 parts in 10 to the minus 22. Otherwise, there would be another kind of oscillation which would increase with energy rather than decrease with energy, which would have been spectacularly visible. And I have 5 minutes left. 5 minutes is a very good time to have left because I don't have too much time, too much more to say. The last slide I have, I think my timing is absolutely perfect. Tiny neutrinos may have broken the cosmic speed limit. That was 22nd of September. When I was in Rome celebrating Luciano Maiani, my dear friend's birthday, his 70th birthday, rumor had it that CERN was going to make a spectacular announcement, which was made during, I think, the course of my flight back home. When I got home, Andy Cohen said, "Remember that crap that you did with Sidney Coleman 15 years ago?" And I said, "Yeah." He said, "Let's do it." And I must say he did most of the work. "Let's do it for these neutrinos." And we realized that it was a rather different process, that superluminal neutrinos. By the way, the superluminality that was announced is 25 parts per million. And we've just been talking about limits of to the 23rd decimal place, and now we're back to the 4th decimal place. This did not look very plausible to us. And indeed, we were able to show that superluminal neutrinos, assuming the, I'll tell you what we assume in a moment, would radiate electron-positron pairs copiously, and the neutrinos emitted from CERN would never have arrived at the Glashow with their original energies. Most of them would have their energies depleted to 12 GeV or less. So that made the experiment, the success of the experiment made the doing of the experiment impossible. It was an example of a reductio ad absurdum, which is a mathematical technique here applied to physics. Now, are there any other ways? And the people have suggested all kinds of crazy things, and they may arise in the discussion. The only one I cannot, step on absolutely is the one of Amelino Camiglia and his crazy collaborators. They have something that they call deformed special relativity, which I would call malformed special relativity, in which has been explained to me by Andy Cohn, because he studied it, because they were bombarding us with complaints, accusing us of being idiots for not recognizing their contribution, which we eventually did in the published paper. What do they give up? How do you reconcile it? They claim there is no violation of the special theory of relativity, that energy is conserved as it always is, momentum is conserved as it always is. So how come the neutrinos travel faster than light? Because we are being foolish. We are regarding energy and momentum not only as quantities which are subject to a conservation law, but we are regarding energy as the generator of space, of translations in time, and momentum as generators of translations in space. In other words, we're saying of a wave function evolves as e to the I et minus px. And they say, you can't do that. There's a arbitrary relationship between the E and P that occur in the propagation of a particle and the E and P that are conserved. And once you make such an assertion, then you can have neutrinos travel at 100 times the speed of light. So they've solved the problem, and we are wrong. I admit it, and that's all I have to say.
When you mention Andy's heroic calculation, what do you mean? Because when I read the paper, I had the impression it was a very plausible combination of dimensional arguments, etc. So did he really make a computation?
Oh, we did the exact, sorry.
How?
I watched him. He did the precise calculation. I watched and checked him as best I could. It turns out that despite our best efforts together, we did make a serious error in terms of losing at one point gauge invariance. We've refined that. That's straightforward. The calculation is straightforward but tedious. The answer we published has to be changed by a factor of 4/5, which has no impact on anything.
No, but besides gauge invariance, you can formulate it once you give up.
Well, when you when you have the choice of screwing up either the propagation of the neutrino or the propagation of the electron. Suppose you screw up the propagation of the electron. Then you have to make sure that current is still conserved. Because once you change the electric current, it's not conserved. So you have to restore current conservation.
Okay,
and then when you do that, it's Andy has the following remark for you, and specifically for you guys at the Institute. He said, if you really want to know the details of this calculation, why don't you invite him to Spain, because he would love to come and visit.
With pleasure, once more.
Okay, that was his message to you. So he told me not to explain things in detail. He would prefer to do it himself. After all, he did the calculations. Good.
Shelley, aside from the experimental evidence, do you have any, are you comfortable with tachyons?
Well, nobody mentioned the word tachyons except foolish people in the newspapers. The neutrino is not a tachyon. A tachyon is a particle that lives within the special theory of relativity. We're talking about departures from the special theory of relativity. We're talking about particles where dE dP, the group velocity, is larger than 1. That means E is bigger than P. In other words, our neutrinos are time-like, not space-like. They couldn't be more different from tachyons. The word tachyon or the concept tachyon plays no role in this whole, should play no role in this entire discussion. So therefore, I could not have given this lecture before the experiment was done.
If the neutrinos
I could not have criticized the experiment before it was done, because tachyons are not involved.
Everybody knows that nothing happens in Italy before quantum. Any other questions? Yes, up there.
Just a comment since you said it jokingly. Just to make the obvious comment that everyone knows, these theories of deformed special relativity are not theories in any conventional sense of the word. There's no Lagrangian. There's no way of even in principle talking about the production of the neutrinos. It doesn't fit into any kind of field theoretic framework. They have problems with the famous soccer ball
Good,
problems,
thank you.
all sorts of other problems. So obviously you didn't capitulate. You just said it jokingly, but it's worth reminding everyone these theories make zero sense.
I couldn't hear him. What is he talking about?
Can you say it again briefly and loudly?
Yeah, loudly.
Deformed special relativity makes zero sense.
Okay, I'll buy that.
There isn't even a theory.
Any other statements? If not, if yes.
So what could be wrong with the experiment?
Well, is there anything wrong with the experiment? If I've told you what we have done, and so far as I can tell, there isn't any, I haven't seen in the literature any sensitive alternative that would explain the experiment. So what I have said to various newspaper reporters yesterday is that if the experiment is confirmed by, let's say, two groups, and there are two groups out there trying to confirm it. There's the Japanese, the T to K group, with their data already in hand, because they're not doing any new experiments at the moment. But they have the data in hand, and they are working on a paper which may or may not confirm opera. And there is the Minos experiment. I don't know what the time scale is for the Minos experiment. Probably take another year at least. But if they confirm it, I am retiring from the discipline of physics.
Okay, this being said, I think we should thank Stanley again. So